on this computer. Okay, all right, so finally, we're in section 4.2 and we're going to talk mean value theorem. Okay, so before we get into mean value theorem proper, we need to talk a little bit for a couple of minutes. Come on, there, about the so-called first derivative test for local extreme values, right? So, so this theorem says that if f has a local maximum or a local minimum value at an interior point C of the domain, then f prime and f prime is defined at C, meaning the derivative exists, yeah, then f prime must be equal to 0. Okay, so one thing I want to, so this is one of the theorems that I would like you guys to learn for the exam, okay? So learn the statement for the final. Now, what does that mean? That means make a note card, okay? Please make a note card with the statement, okay? And I would also add some examples on the back of this, right? So let's just first talk about when this is going to fail. Okay, so first example, when this is going to fail, if the function so they're essentially, okay, there are two hypotheses, right? I think it was a little bit cuckoo last time, so I was telling you that there are three, really two hypotheses. Two hypotheses, or two assumptions, hypotheses here. Okay, assumptions. Where do you find assumptions of the theorem? Okay, you guys, you can speak. You can speak to me. So where, if you're looking at the statement of the theorem, where do you find assumptions or hypotheses?
One of them is the first part, the assumption that it has a local minimum or maximum.
Okay, now what do you use? What gives them away? What are the keywords that give away that here comes an assumption?
Putting in conditional sentence.
Conditional, exactly right. Is this Mel?
Yep.
So what is the key word?
If then.
If, that's right.
No.
So these are the things that come with if, right? So it's like every theorem has the form if. Okay, and here we have A and B, right? Okay, then C. C is the conclusion. This thing is my conclusion. Conclusion. And the other things are my hypotheses, both A and B. I am using a tablet which is blind, like a graphical tablet, so sometimes it's hard. So these are two my assumptions. Assumptions. Okay, so I have two of those. So what is the first one? It's kind of complicated. Maybe the second one is easier to state. So let's start with the second one. Notice how I used the symbol for and. Maybe I shouldn't have used the symbol for and. Okay. Okay. Okay, why am I having such a hard time controlling my, what is going on? Draw. I swear I had no
You
problems.
selected a small box in the bottom right of the screen.
No. I'm trying to. You guys, I have the annotation palette. No, this is ridiculous. I had no trouble controlling anything today in my.
You're trying to put down like a text box wherever you click.
I'm not trying to do any of this.
You may have selected the wrong tool by accident. Anywhere you click, it wants you to type out words. It wants a text box. You may have just clicked the wrong tool.
I don't understand why it's not letting me select the drawing tool. After I used an eraser, I'm completely like freaking unable to select.
Just check your tools, see what's highlighted.
Okay. Okay. Why is it doing this? I had none of these problems yesterday and today, and like on Monday, I had exactly the same problems when I what the heck is going on? This is ludicrous. Draw. Okay. So I have my drawing box. Okay, draw. Okay, I'm unable to select, and I have no idea why this is happening. I'm telling you, like, this is not, it's not because I'm sick or anything like that. It's, I had perfect control.
Feel better?
No, it's not. What the hell is going on?
Is the drawing in the Zoom program or the slideshow program?
I'm drawing in the Zoom.
Oh.
The slideshow program actually doesn't let me. I don't think it lets me draw over the top.
So you can make notes.
God.
What's going on?
Oh, I just realized that I could annotate on this the whole time.
You can what?
What's going on?
I didn't know I could annotate. I thought I've been trying to. Every time you've been saying you can annotate on the thing that you're showing us,
Yeah.
I've been trying to find it in like Google Docs or something.
No.
And I just clicked on the thing above.
There's the live interaction. You can annotate over the live interaction. But in addition to that, I gave you separately ability to annotate in edit the Google Docs. Okay.
Yep.
Pen. Okay, I can draw over the slides. I'm going to do that. Okay, so now I just need to share this thing back up with you. how do I get, did I end? Okay, I've stopped sharing the screen with you guys, right?
Yeah, I don't have it on mine.
Okay, so I will, okay, so let me try to restart this, and I just want to do PowerPoint. Okay, I think it's the two problems fighting for control with one another. I think that's what's been going on, honestly. So I'm gonna try like that, and hopefully I can. Okay, pen. Okay, all right. Okay, there we go. This should work. I don't know if I'll be able to erase, but you know, we'll just hope for the best. So okay, so assumption 1 shall remain kind of mysterious for a second. What is assumption 2? And remember what I said. I said that you have A and B, right? Imply C. Or if A and B, then C. Okay, so I want to know what is my A and what is my B. Okay, so just reading this theorem statement, can you guys unscramble for me this B, this mysterious B part?
Is it just if A and C, then B?
You guys, look, you have a theorem. If f has a local maximum or minimum value at an interior point C of its domain, and if f prime is defined at C, comma, then f prime of C is equal to 0. Okay, so the easy part is maybe the conclusion, then. So what is the conclusion? So what is the statement C? Capital C. These are statements. Sentences, okay? That's a sentence. So what is that sentence? Okay, somebody's chiming into chat. F prime is equal to 0. That's the conclusion. Okay, very nice. Okay, so that's C. All right, very nice. Okay, we have F prime of C equals to 0. This is my conclusion. Okay, what about the other parts? What about this A and this B? So let's start with B. That's a sort of easier thing. That's my B.
B would be if F is defined at C.
Okay, so look, I have A and B, right? Look at the structure. If F has a local maximum or minimum value at an interior point C of its domain, and then you have and F prime is defined at C, not F, F prime. So what would be the shorthand for that? F prime.
I don't remember.
How do I say F, the derivative of F at C? How do we write it? By the way, I think you can take over. You can maybe try to draw on this. I don't know. Okay.
Are you talking about what you already have?
F prime of C
Yeah.
exists.
Oh, yeah, okay. I thought
So,
yeah, that makes sense.
this is what this means. F prime is defined at C. That simply means the derivative, this thing, F prime of C exists. Who drew in green color? Who drew in yellow color? Okay, you can get participation. That's right. So if 1 and 2 hold, then the conclusion also holds. Okay, so what about A?
That would be, may I write it?
What about the first part?
Yeah, may I
The
write it?
first part
Or
of
at least
the
underline it.
statement.
Is it just A and B or C?
Anybody?
The first part is just if F has a
What's the
maximum.
statement A.
Oh, mic on?
Hello?
Is my mic on?
Yes.
Yes.
Is my class
it
still
is.
there?
She can't hear us.
Is
Yes,
there
muted.
anybody out there?
She.
Gotta get a hold of that.
There is. Okay.
Oh, I'm not gonna try and draw.
Because
Never
you
mind.
muted yourselves or what?
I have a tablet, so
Okay,
it's easy.
I'm
Sorry.
going over my slides. So why can I not hear you?
Oh, why can't I chat?
Okay. Somebody's typing. I wonder
Ha!
I did not mute anybody. I did not mute you, not on purpose. Nope. Nope. I have not muted anybody. You can hear each other. I don't know why. I don't know what's going on. No, everything is plugged in. Okay.
I'll just write it.
I think it's the evil Microsoft.
What is going on?
PowerPoint.
I'm seeing like flashes of green.
You can't hear us. Okay.
Black. Is it
Good.
just me?
But I mean, I can hear you, but can somebody provide me with this part that's missing? So we already have the if, but okay. F local max. Or
How can you draw so well?
I have a tablet.
Oh, okay, that makes sense. I'm like trying to do it with the
Garrett, I
Alright.
thought you were being sarcastic.
But where?
No.
No, he drew so he just wrote it so fast.
Can you guys erase this blue statement? Whoever wrote it. It's not incorrect. It's just incomplete.
So local max at F prime and C.
So I would put it in.
Yeah, type it in chat if you want her to hear you.
If
The interior point.
Can she still not hear us?
C.
Yes, she still can't hear us.
Okay.
Wonders of
Houses.
technology.
This is
Maybe her mic broke. No, maybe her headset something.
I bet she has her
Something
headset
happened.
half unplugged and she doesn't know.
External.
Oh well, that's fine.
And
She can probably hear it.
interior. She is not an endpoint. Not.
Nah, she's probably not messing with us. Okay.
Okay. Very nice, kitty cat. Very nice. You guys, do you want me to knock out your annotation powers? I can do it. I actually know how to do it. A very cute kitty. I have a new message.
Wow. She doesn't like fun at all, huh?
Okay, I checked everything. People were like telling me, I don't know why I can't hear you guys. I don't know.
Oh, I thought she heard you. I was like, oh no.
With people
I thought she heard me because I had like a cat in my lap. And I just thought.
And because everything
I looked behind me. I thought my cat was behind me. But it was a kitty cat. I'm
on purpose. Maybe not. Maybe it's just that I was not using PowerPoint, and there could be some kind of weird conflict. So,
can you hear us, teacher?
from a benefit of a doubt. The problem is,
Nope.
if somebody knows how
This
to
is a shit
get
show.
rid of everything I've written in PowerPoint, that would be a huge boon because I don't. I don't know how to clear my screen in PowerPoint.
Oh my god.
Using Zoom, that was fine, but in PowerPoint it's just impossible.
Clear. It says clear. Oh, in PowerPoint.
Hey, guys, did she mute Zoom? Is that a possibility? She just like outright muted the app?
This,
Possible.
if I escape full screen here.
Now
I
our
mean,
microphone is
what?
gone.
What says she doesn't just press a button on her keyboard that just mutes the sound?
Well, there are a bunch of hotkeys.
It's
for
still
this.
recording. Yeah, that's fine. I know.
I bet she just
I
muted the
can't
sound
wait
on
to
her
see the
computer.
recording class. It's gonna be so fun.
Unfortunately, sometimes weird technological doo-doo that's happening. I don't know why. I've encountered these problems before with.
This is why we take notes ourselves.
Yes. I wonder if you can. I wonder if you. Yeah.
Can you see my slides?
No.
Can you answer in the chat? Or did I stop? No, you can't. Okay. All right, so I'm gonna share the screen with you. I'm just gonna share the full screen with you. It's not working. But... Okay, PowerPoint sucks. I'll get out of it next time. I just won't use it.
Did she just mess with her computer
so
volume and
share.
just turn it off? I have a feeling that's something that happened or something like that.
I'm trying to press every key and see. 1, 2, 3, 4. Whoa.
Yeah.
Oh,
Okay.
she did that.
The annotation tools here. Okay.
Yeah, her volume's off. Look at the top bar. Her volume's on 0.
Oh my god. Oh my god.
Yes, of course I can mute and unmute the class. My volume is not all the way down. Oh.
Yes, it is.
Boy, it is.
Hi.
How did that happen?
I'm circling it. Do you see?
I did not. I mean, I promise you guys. Okay, so somebody's making
stop scribbling.
Okay. Okay, thank you.
Very fast.
Yes, I know that I can mute and unmute the class. My volume is down. It was down and now it's up. I have no idea why that happened. I swear I did not touch the volume. There may be some controls on my pen, which I have not like finished programming yet. Okay, let's get back to the lecture. Okay, you guys, oh boy, this is really hard. Okay. All right. Okay, I'm gonna close the chat. Okay, back to the pencil, back to this. Okay, have a look at this. So I'm gonna change things a little bit. Here, the picture. So A to B. Okay, you can see the closed interval from A to B. Yes? And C is an interior point of the domain. It's not one of the endpoints. Yeah? Right, so now I'm gonna look at the secant slopes. Okay, I'm gonna attempt to compute f prime at C. Okay. Now, does this look familiar? That this is the limit as h goes to 0. I'm gonna say from the right. F of C plus h minus f of C divided by h. Okay. And now let's see. Let's see that, you know, h is going to be this distance. Okay. Can somebody draw the secant line that corresponds to this in this picture? Just this. Okay, so there's an implied y-axis. Very nice. Go on, go on. I don't think we're interfering with one another. Very nice. That's right. You know that there is in the drawing tool, there is a straight line tool. So you can actually draw perfect straight lines. But that's a very nice idea. Yeah? Okay, now we're thinking of shrinking the h. Okay, can somebody else, using a different color, draw a secant line when h is half that size? So I'm going to mark the new h. Going up. Well, you need to go up to the graph. Yeah, that's right. That's right. Don't forget, when you go to the draw tools, right there, next to the squiggle, there's a straight line. You could just grab a straight line. Very nice. Very nice. You can, yeah, that's the idea. Okay, very good. Okay, now, what can you tell me about these slopes? Are they positive, negative? What are the slopes of these secant lines?
They are negative.
They are all negative. These guys are all less than 0. Negative, yeah. Everybody can answer into chat if you wish. Yeah. I agree. Yeah. All right. Now, very quickly, I'm going to try to go the other way. Now, H is going to be, I'm going to change the color on that, and I'm going to use magenta. And now H is going to be negative, and I'm going to use H like this. So this distance is, so to speak, I mean, from here to here is going to be H is negative, right? So this is C plus H, but it's to the left of C. H is negative. Okay. Can somebody draw a secant line for me that corresponds to this difference quotient? Well, I really like the dot, dot, dot. Can you go up to the dot, dot, dot? And there's a problem.
That
You
may be
drew a
difficult for
tangent
people to
line,
do.
not a secant line. Okay. So the line is goofy. There's something wrong with that.
Oh, that's a regular pen. There we go.
Okay, so please make the, so I don't, make the black line disappear. So it has to go through this point, the point that I'm making magenta. And it also has to go through that point. It's a secant line. Okay, it's a little bit off, but you know.
Hey, kitty.
We have a kitty cat. Okay, so yes, that's right. So I have two, yeah, they're pretty close. Okay, it's not necessarily easy. Okay, make them disappear. Okay, can you, what can you guys tell me about these slopes? So they're gonna be in magenta right now. So now H is negative. H is negative. F of C plus H minus F of C divided by H. If you're talking to your kitty while you're also talking to us, please mute your mic. What can you tell me about the slope of this red, beautiful secant line? Very nice. Positive, negative?
Positive.
It's positive. Okay. Well, okay. So quickly, if I make a H half that size, okay? If I now shrink the H, and that's my new negative H. The new H, okay? Yeah, that's right. Okay, so that's the intersection.
That's a good way to do it.
Uh-oh. Yeah. So, okay, so you found where this vertical line intersects the graph. Very nice. Okay, that's the secant line. You see, it's also positive, but it's less positive, yeah?
It approaches 0.
Well, okay, so here it's true. They have to approach 0, but notice why this has to be true. Notice that what we have on the right-hand side, I have a limit of a quantity that's negative, right? So my f prime has to equal the right limit, yes, as h goes to 0 from the right, of the difference quotient. The difference quotient, when you look from the right, is negative. Okay. Also, the derivative has to equal to this limit as h goes to 0 from the left. Correct? Because the derivative exists if and only if these two limits exist separately and they agree with one another. That's right. For an interior point, I'm not talking about endpoint, I'm talking about interior. At an endpoint, all you need is one-sided derivative. Two-sided derivative is not needed. But here, we have this funny situation going on, okay? So how can this be? Okay, so basically, I have this. One number, f prime at c, is equal to limit as h goes to 0 from the right of one function of h, okay? And this function is negative. And then it's also equal to limit as h goes to 0 from the left, same function of h, and this function happens to be positive, okay? These numbers are negative. These numbers are positive. How can they have the same limit? And the words have already been spoken. The only way they can have the same limit is if this common limit is 0. Okay, here's an example for you. 1 over h. Oh, sorry, not 1 over h, 1 over, sorry. Example. So here's an example for you. Okay, so if g of h is simply equal to h, right? Then when h is greater than 0, g of h is also greater than 0. When h is negative, g of h is also negative. Yes? But as h goes to 0, limit as h goes to 0, g of h is simply equal to 0. Okay? So you're thinking like, you know, h is 0.1, 0.01, 0.001, etc. All positive numbers, but they're tending to 0. And then if I go from the negative side, they're also tending to 0, and they meet in the middle. They meet at 0. Okay, is that clear? Okay, so that's essentially the proof of this theorem. Okay, now this is called, interestingly enough, this is called Fermat's theorem. Oh, I managed to move it out of the way. So this theorem has a name. You don't need to remember that name, but I think it's kind of useful for your general education. So this is called Fermat's theorem. I called it Weierstrass theorem last time, but that was a different one. Fermat's theorem. It's not Fermat's last theorem. Okay, so now we're going to move on, and okay, there's a question. Am I not sharing PowerPoints with you? Oh, you would like me to share PowerPoint. So Leo is asking me to share PowerPoint. I can't, Leo. I can't write over them. I can't control the way it's happening. Is it not big enough? I mean, maybe I can increase the size. Is this better? I wish I could do a PowerPoint presentation, but I'm gonna have to kind of, oh, after, but they are shared with you. All the PowerPoints are on Google Drive. Absolutely. Yeah. They've been sitting there for longest time. They're like in your lecture notes. Yeah. Yes, but please don't use them to make cards, to memorize stuff. You should, I mean, you can look at them, right? But what you should do is you should write the cards for memorizing. You should write them with your own hand. Okay, that's very, very kind of important. All right. So clear over drawing.
Because that way you can read them and it helps with memorization.
Absolutely, it helps you. I don't know, there's some kind of magic connection between our hands and our brains. I don't know, maybe it's called the arm and the rest of the body. No, but there's definitely some kind of feedback thing going on. Okay, so now we're going to move on and prove another theorem. I'm sorry, today's going to be a theorem heavy. It's called Rolle's theorem. Okay, and the way I'm going to introduce you to it is like so. So have a look at these two functions. Okay, so these are two different f's. I wish they were smart enough. I mean, if I were making this textbook and the slides, I would give these two functions different names. So maybe I can change that. I'm going to call this G. Okay, so just to say that this is, well, maybe I'm not that smart. I should have changed the other one. Sorry, clear all my drawings. I'm gonna, because there's just less stuff to write, I'm gonna change this one to G, okay? I'm gonna change the name of this function to G. Okay, and the other one is gonna be F. These are two different functions, right? And clearly they're sitting really over two different intervals, but we can pretend like this is just a kind of a scaling factor, yeah? So, all right, I have a closed interval, AB. Now, what can you tell me about this function G on this interval? So just say, like, please speak, you know, hopefully I can hear you.
I'm sorry to again illustrate this. The disciple, so the Zen master asks the disciple in their usual seemingly fierce way, do you understand Zen? And the disciple says,
okay, I have Eckhart Tolle speaking about Zen in the background. I have no idea
and the
why.
master says,
Just somebody get into my computer
I.
and start playing with my funny.
It's not, so it's not, you can't get Zen through conceptual understanding, and you cannot find the meaning of life through conceptual understanding if you
turn your volume all the way up, so now there's
relinquish your desire
like
to understand conceptually
happening.
and access that in you which is beyond
Turn your
concept,
PC volume down.
then you find the meaning of life, but you may not be able to say what it is.
I'm trying to kill a window which is running the thing.
The question comes from what you said so beautifully, Eckhart, that you evaluate, you use your five senses to determine your reality.
Okay, I found the window. I just locked out and I found the window. This was running. At least it wasn't, you know, anything embarrassing. Good. Eckhart Tolle is not the worst company in the world. Okay, back to lecture. Okay, you guys. So hopefully I can hear you when you speak. And then you can also is unstable. I have an unstable internet connection. Don't know why they think it's unstable, and I need to quit this. I can safely quit this for now. Okay, what can you tell me about this G, just from the looks of it? Some words that nice words that you can say about this function.
It has no derivative at C.
Oh my God, that is just so wrong. Who said that?
Derivative is equal to 0.
Ah, very different. Very different. No derivative means that there's like a vertical tangent line, there's a corner, or there's maybe a discontinuity. That would mean that there's no derivative, or these wild oscillation. So, okay, so G, okay, is, so derivative is 0 at C. What else? What about throughout the entire interval? How would you characterize the function?
It is exponential.
This one? The one that goes up and down like that?
Yeah.
Seriously?
Yeah, it's just a shifted inverted exponential.
Exponential? No, exponentials look like that. The ones that are growing, they look like that and they grow forever, or they decrease like that. Exponentials look like that. So this is quadratic, a parabola. So it's a shifted inverted quadratic. But I don't want that level of precision. I want, the words that we've been using, the kinds of words that I've been asking you on tests. What can you tell me about it? So is it continuous? Yes. Yes, it's continuous, absolutely. It is continuous. What else? What other words do you know that we've learned in this class? So on the entire interval on AB, right? What about the derivative? Does the derivative exist at every point in the interval? True? No, not true? Okay. Question. Does g prime of x exist for every x between A and B? Okay, please everybody answer into the chat, yes or no? You can do it privately if you're worried about being wrong. Yes, yes is correct, it's the right answer. Yes, g prime of x exists for every x between A and B, including at the endpoint. So what does that mean in terms of the function? How do we call functions which have derivatives at every point of an interval? Is what? What should I put here? You can speak into my ears or write into my chat. When the derivative exists at every point of the interval, we say that the function is something on the entire interval.
Differentiable?
Differentiable. The function is differentiable. Differentiable. Okay. Differentiable. And it's also differentiable at C. Okay. Also differentiable at C. At C, meaning that G prime of C exists. Okay, and lo and behold, I think it was Brian, if I recognize the voices correctly, Brian told me that G prime of C equals to what?
0.
0. Remember, very different from not existing. I know it's very tempting to say when something is 0 that it doesn't exist. No, in math, 0 has its very own peculiar existence. Okay, clear? Now, can you guys tell me, what about this F in the next picture? Are all these statements true for F? Am I dealing with a closed interval? I'm dealing with a closed interval. Is the function f continuous? Yes, it's continuous. Is it differentiable? Yes, it's differentiable. Now, from the looks of it, it's probably some kind of a polynomial. What degree polynomial it probably is? Well, look at the number of humps. 1, 2, 3, and I bet you it has a fourth hump. So a polynomial which has 4 humps has at least what degree? Do you guys remember? This is from pre-calc.
Five.
So yeah, that's right. It's like quadratic has 1 hump, yeah? So degree 2, so the number of humps is 1 less than the degree of polynomial. Yep, that's exactly right. So this is probably a quintic. It could be higher than the quintic, right? At least. So I would say that the degree here is greater than or equal to 5. Well, just from the fact that this is kind of bending up like that. Okay. We're going to clear the screen. I lost my ability to annotate. Okay, clear all drawings. Okay. So now there is one more property that is the same about these two functions. Okay, can you guys stare at these pictures and tell me what is the same about function f down below and the function that I call g, which is a little bit higher? Okay, let me give you a hint. There's something about g of a and g of b. Talking. Somebody's talking, but I cannot hear. I wonder what's going on again. No, I have my volume is all the way up. Okay. Tangent equal to 0. At C, the tangent equal to 0, and here we have C1 and C2 and C3. Can you guys, what is funny about G of A and G of B and F of A and F of B? Do you notice?
They have the same y value?
The same y value. Do you guys see this? This is G of A, which is equal to G of B, yes? And this is F of A, which is the same as F of B. They also kind of made them look equal to one another, but that's just kind of, you know, an accident. Okay, so what's really important is that the values at the endpoints are equal to one another. Okay? So basically the theorem tells you that as long as you have a function that goes up and down, or down and up possibly, yeah, because if I could have his brother that looks like this, I would have a similar situation. Then somewhere there is going to be a point where it has to flex over, and at that point the tangent is going to go flat. Okay? That's going to be the point where the value of the derivative will become 0. Okay? Okay, clear all drawings. So we're gonna go. So that's the statement of the. Oh yeah, it's not displaying the pictures. You know why it's not displaying the pictures? Because oh, I made a mistake. I quit my Google Drive stream on this machine and now it's not displaying the pictures. Okay, I know how to work around this, but it's gonna take a minute. Okay, so bear with me. Okay, we're gonna go to here. We're gonna go to shared folder. Okay, by the way, Leo, so this is, you were asking me where to share the slides. Right here, this is on your Google Drive. You actually have access to this. Under lecture notes, if you go to lecture notes, you go to chapter 4, PPTX, and this is where the slides are, yeah? So I can navigate these guys pretty easily. Okay. So I'm sorry, I'm gonna have to click through. Oi, that did not work well. Where did we go to chapter 7? No. Okay, I need this. I need that. Oh, there we are. Okay. Sorry, close your eyes for a second. I'm gonna zoom through a bunch of stuff. Okay. Here we are. Rolle's theorem. Okay, here we are. So this is the statement of the theorem. Okay. Suppose y, a function of x, is continuous over a closed interval AB and differentiable at every point of the interior. See, the differentiability does not have to extend to the boundaries. Okay. So, but what has to be true is f of a is equal to f of b. Then in that case, there's at least one number c in the middle where f prime of c is equal to 0. Okay, so also to memorize. So I'm gonna just briefly say to memorize. Okay, now I'm going to give, in the next slides, I'm gonna give you an example of where it is almost like the F and G that we worked with before, but it's actually a little bit different in the sense that right there. So here's an example where Rolle's theorem works perfectly nicely. However, the function is differentiable, is not differentiable on the closed interval. So I would like you guys to help me out. Okay, so first, okay. So I'd like you to write the largest interval where this function is continuous. Continuous. And you're welcome to write right here. So it's continuous on some interval, it's differentiable on a different interval, and the last question is, okay, is, okay, f of -1 equal to f of 1. Okay. So I want to see what is my interval AB. Okay, I don't understand these brackets. I don't know if it's a closed interval, open interval, what? So which one is it? Continuity is required on a closed interval. Closed. It looks open to me. Make it closed. Make it closed. Okay, so correction. This needs to be corrected. It needs to be closed interval. Yep, closed interval like this. -1 and 1 were right. But continuity has to include the boundary points. Cannot be discontinuous at boundary points. Look, this is the function. This is y equal 1 minus x squared. Plug in, so let's just call it f of x, yeah? What is f of 1? Very nice, very nice. The person with a purple pencil. That's correct, okay? So it's differentiable. Thank you, Charlie. So it's continuous on the closed interval -1 to 1. It is differentiable on the open interval -1 to 1, okay? So can you guys tell me what is f of 1? It's 0, that's right. Do you guys see this? I plug in here 1 for x, and I get square root of 1 minus 1, which is 0. All right, f of 1 is equal to square root of 1 minus 1. It's a big fat 0. What is f of -1? Well, it's also square root of 1 minus, okay, let me write it out in longhand. -1 squared. -1 squared is still 1. 1 minus 1 still gives me 0. Okay, these are just the y values, 0 at both endpoints, yeah? So all three conditions of Rolle's theorems are satisfied. And lo and behold, right there in the middle, at 0, at x equal to 0, you have a spot where the derivative becomes 0. So the slope of the tangent line is 0, or the tangent line is horizontal. Okay, can somebody tell me what is the problem with f prime of -1? Okay, you're welcome to type it into the chat, for example.
Wouldn't that create a division by 0?
Okay, it's undefined, okay? In our parlance, because we're well educated at this point, the derivative at -1 is undefined. What can you tell me about the tangent line? Does it exist? I would say that the tangent line exists, but it's very particular. It's vertical. Do you guys see this? At -1, there's a vertical tangent. And the same thing is true at 1. There's a vertical tangent line. Okay. Therefore, but the Rolle's theorem holds perfectly correctly, yeah? So therefore, it's sort of an example of where it's not necessary to have differentiability over the entire interval. It is enough to have the function be differentiable only on the interior. Okay, I'm going to clear this, clear all my drawings, and I'm going to go back some for a second. I want to show you examples of when so there's some examples when at least one of the conditions fails, okay, and the conclusion is false. Okay, so, all right, so let's look at this one first. Okay, I'm gonna switch just for kicks and giggles. I'm gonna switch to this, to a yellow, can you see? All right, so starting with this, okay. Does this one have, is it true that f of a equals f of b? Is this true? You can speak or just type things into chat, whatever you want.
No, it's not true.
Please, you don't use okay, I'm gonna change to blue. Okay. Is it true that f of a equals f of b? Not true. Any other opinions? Okay, look at f of a. So if I say that this is 1 on the scale, right? And this is 2. What is f of a here? Looking at this picture, f of a is equal to, can you guys type for me into chat? Everybody who's here, please type in, what is f of a? It's 1. Do you guys see this? Yes, okay. What about f of b? F of b is also 1, that's right. Do you guys see this? Okay, so how we went up to the graph and then over to the y-axis? Yes, this is the y value. So is it true, I'm gonna ask this again, is it true that f of a equals f of b? Yeah. True. Yes? Okay. F of a equals f of b. Is it true that f prime of x exists for all x between a and b? Not at the boundaries, but on the interior. Is it true? True or not? Okay, I have 1 vote for yes. Can you guys raise your hands? Okay, if you think the answer is yes, please raise your hands. 1, 2. I get 2 votes for yes. Okay, if you think it's no, please raise your hand. Hello, I have 9 people, 9 participants. 2 have voted yes, and other 7 are keeping silent. No, you don't get an option. 2 answers, yes or no. Yes, okay, so privately, so no, I mean, can you see each other, like, can you see how you vote? I don't think when you raise your hands, oh, maybe you can't see it. Okay, then don't type it privately, okay? You can answer your question privately to me. Okay, I have 3 yeses and 6 suspensions. Right, I agree with this yes. Okay, I have 4 yeses, 2 of them private. No, one has been made public. It's correct, it's true. The answer F exists. Yes, it's true, yes. All right. Is it true that F is continuous? F is continuous on open interval from A to B. Is it true? Open, not closed, open interval from A to B. All right. Continuous in an open interval. Okay. All right, you guys, this function is continuous on this open interval. When you ignore, right, when I consider something on an open interval, it's like this A does not exist. It's like I only look from here to here, and everything else in the universe simply does not exist, you know? There's nothing out there. Boom, 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 boom. Okay, nothing matters. Nothing really matters to me outside of this interval. Do you guys understand me? Yes? Okay, everybody agrees now that it's continuous. If I just, like, it was a Stephen King novel where there's things that were eating reality. Like somebody ate reality outside of this little interval from A to B. Okay, in that case, this function is continuous, yeah? All right, so it is true that it's continuous on AB, and yet, does the conclusion of the Rolle's theorem hold? Is it true that there's some point C where the derivative is 0? True or not? Okay. All right, true or not? True or not? Okay, f prime of C equals to 0 for C between A and B. Okay, vote. Please go to your chat and vote privately or publicly, whatever. Not okay. I have 1, 2, 3, 4 no nays. 4 nays and 5 people are keeping silent. Okay, 5 nays and 4 people are keeping silent. It's correct. No is correct. Okay, so what gives? What's the problem? The function is differentiable on an open. Okay, wait a second. So we were studying this lovely theorem. It's called Rolle's theorem. Yes, we've been hard at work on it. We've discovered that there's this function which obeys pretty much all of the assumptions, yet the conclusion does not hold. What's the problem? I don't think there is really a problem with the class. I mean, the class has shrunk a little bit, but that may have to do with our technology issues or with my technological inaptitude. So, okay, here's the theorem. We've looked, it looks like maybe the assumptions hold, but the conclusion doesn't. I say it's a broken theorem, let's throw it away. Why am I wrong? Aha, that's right. Okay, so look right here. The theorem requires continuity on a closed interval. So continuity must extend up to the boundaries. If it does not extend up to the boundaries, then nobody promised you, there's no legal obligation for the conclusion to hold. Okay? Got it? Okay. So now that we've worked really hard, can you tell me what's wrong with the other two? So can you tell me what fails at B? And okay, so in B, so in C there's a corner, right? Meaning that the function fails to be differentiable. But in B, it's not removable discontinuity. What kind of a discontinuity exists in B? What's the problem here? Jump, that's right. Okay, so this one fails to be continuous here. Yeah, this one fails to be differentiable here. Okay, and let me draw one more problem for you, and it's going to be a completely different conclusion. Sorry, completely different condition failing. Oi, no. not good. Well, okay, like this, like that. Okay. All right, so what if I have something that looks like that? And this is my A, and this is my B. I say this function, let me see, F, G, I'm gonna call it G. I say G is continuous on the closed interval AB. Okay, G is differentiable on AB. Yet, are there any points between A and B where the derivative goes flat? No, there are no points. You guys see this? I would say that the slope of the tangent line is always positive here. It's never zero. Yeah, so what's the problem here? What fails? Which one of the assumptions of my original theorem fails? What assumption of Rolle's theorems fails in this case? Haha, okay. F of A is not equal to F of B. Okay, do you guys see this? F of A is not equal to F of B. The function keeps on increasing, so nothing kind of makes it flex down like that. Okay. Okay, so I hope that this is really, really clear to you. Clear all drawings. Okay. All right, so now we're gonna talk about something called the mean value theorem. So the mean value theorem is a kind of generalization of Rolle's theorem. Okay, in the mean value theorem, the statement is right here in front of you. I'm going to read it to you, and I'm going to write, okay, that I want you to memorize this for the final. Okay, so look, it has the same assumptions, almost. F of x is continuous over closed interval AB and differentiable on the interior open interval from A to B. The only thing that's missing here from the assumptions is nobody's asking for F of A to equal to F of B, right? And the conclusion is also different. It's not saying that the derivative is equal to zero somewhere, but it says that the derivative is equal to, what would you call this object? It should be very familiar to it.
Quotient.
It's a difference quotient, yeah, difference quotient, difference quotient, also known as slope of difference quotient using A and B, using endpoints. Yes, and geometrically, it's a slope of what? What kind of line? It's a slope of what? Nobody? Chat? You want to type it into chat? It's okay to be wrong.
Tangent line?
Zero.
It's not a tangent line. Okay, this is going to be a tangent line somewhere, but this is, okay, so let me see what my chat brings me. Secant. It's the slope of the secant line, secant line through the endpoints. So through a comma f of a and b comma f of b. Okay, so what it's telling you that there must be some point on the interior where the derivative of the function, meaning the slope of the tangent line, is equal to the slope of the secant line through the endpoints. Okay, so I'm gonna clear this beauty, clear this annotations, and we're gonna look at the next picture. And the next picture simply expresses this idea. All right, so you have a function, and this function is continuous, right, throughout the entire AB, and it's clearly differentiable. It has a nice slope everywhere, yeah, including at the endpoints. Okay, now we draw the secant line through the endpoints, yeah, a comma f of a and b comma f of b. Through these 2 points, we draw a secant line. Now I'm going to attempt. I don't think I can. I don't think I get a moving line. Look, if I could just make a copy of this line and move it, can I just make a copy and then move it? So let me try to match it. So if I match this line, right? So I made a line that's parallel to this. And can I just move it? I can't move it. If I could move it, right? Then I'm just gonna have to like kind of guess. Look, if I could move this line here, you see that just about here, right? I could draw another parallel line to it that's going to have the same slope and is going to just touch my function. Okay, so right here, okay, there's going to be a point of tangency, and this, when I drop down from here, this is going to be my C. Wait, I need to use, I need something bendier than what I have. The C is going to be right here. Okay, erase this line. Okay. So indeed, you see how this is very similar to Rolle's theorem. In the Rolle's theorem, the function, so basically, I mean, the proof of this is very simple. Is that you write down an equation of the secant line, okay? I call it g of x, the secant line. It has this equation. So y minus f of a, right? I'm using this as my base point, is equal to its slope, which is f of b minus f of a divided by b minus a times what? You guys tell me. Can you help me? Can you help me finish this process? This is the slope of the secant line. This is my slope, m. I'm yes. Oh, I hear a connection. So what should I put here?
X.
X minus. I need to reference to this point.
A.
X minus a, that's right. Look, what this is saying is that if I take any point on the line with coordinates x comma y, then the slope using this point is going to be the same as the slope of the secant line. And how do I write the slope? Is y minus f of a divided by x minus a has to equal m. Do you guys see this? And then you just simply multiply x minus a, and you get to this expression. Do you guys? From here, it's a simple multiplication by x minus a, and you get that expression. Do you guys understand? What I'm trying to say is if I have like a point x right here, okay, and a corresponding y, yeah? So this has coordinates, sorry, has coordinates x comma y. So this point on the line has coordinates x comma y, right? Then if I make a slope, okay, using rise over run between these 2 points, okay, how could I compute the slope? It's the rise, y minus f of a divided by x minus a. That's the slope. So this slope has to match the slope of the tangent line. Oh, sorry, secant line. Is that clear? Okay, I want to hear something like, yes, I get it. Okay. Yes. I got a yes from Charlie and no more yeses, but I hope that, yes, clear from Brian. Something like a smiley face from Wade. Okay, from Stephen. Okay, so now I'm gonna make a new function g out of this using, so I'm gonna say that g, okay, so I'm gonna use this y, yes? That's going to be y is equal to this. So I'm gonna solve for this y. Okay, so I say, okay, well, I just take this y is equal to f of a plus slope of the secant line, right? I'm going to call it m just for a second, but m is that difference quotient times that. And I call this whole function, this is called g of x. Okay, clear? Right, so now if I just take this g of x and I subtract it from my f of x, clear all my drawings. So what do you think is going to be a picture if I take, this is f of x, yes? F of x minus g of x. If I make a new function, I subtract. So y equals f of x minus g of x. Can you guys guess what the graph of this will look like? Well, g of x has this graph, yes? So I want to say, yep. It's not going to be quite a line, no. Okay, so let me, let me point something out. So what is g of a? G of a is the same as f of a. Do you guys see this? It has this value, because the yellow line goes through this point. G of b is f of b. So they have the same, these two functions have exactly the same value at a and at b. So what happens if you subtract them? So what's going to be f of a minus g of a? Yes, 0, exactly. So this is going to be these values, yes? But do you understand that, like, okay, so right here, at this point, this difference between these two functions is going to be simply the height of my new function. Right there, at this x value, this difference, f of x minus g of x, is going to be the height of my function. Right here, it's going to be this height. So if I were to go like this point by point, I'm going to have something that goes like that. And then I can just connect the dots. Is that clear? That this is the graph of y equals f of x minus g of x, where g of x is y equals g of x is this yellow, has this yellow graph. Clear? I'm sure it's not exactly clear. It's something that you guys might have to watch again. All right, so let's, so this is the last thing we're gonna do, okay? I'm gonna clear the screen. I'm gonna clear the screen, and I just want to show you one example of what to do with this. Clear all my drawings, okay. Okay, so here's that picture again, okay? You have f of x, okay? That's the blue line. You have g of x is the yellow line, and their difference is represented by this red line. Is that clear? Does this picture make more sense to you now? Have a look. Yes or no? Yes, okay. I got a couple of yeses, yeah? But notice that how at this, in this new picture, this right here, right, this red function, this h, now satisfies the conditions of the Rolle's theorem, yes? Okay, this function for h, which is the difference, I have h of a is equal to h of b, as Rolle's theorem demanded. H is continuous, it's differentiable, it's continuous from a to b. So continuous on AB, differentiable on, actually it's differentiable, sorry, it's differentiable on a closed interval, but you know, that's all I require, all the theorem requires is that it be differentiable on the open interval. And this, that means Rolle's theorem is satisfied for this h. Okay, so that's telling me that there's some c where h prime of c is equal to 0. And indeed, yeah, if I just take a straight line, right, through like just about here, right? Well, okay, I'm gonna have to try again. It's kind of hard to draw tangent lines. Hopefully I can erase the other one. Oh, I erased them both, no! But I hope you understood, right? That there a tangent line right at this x is 0 for this function, for this red function with the red graph. The function h with the red graph has a 0 derivative. What does that mean for the other ones? Okay, look, h prime of c is simply equal to f prime of c minus minus g prime of c. Okay, so let me clear this. It really wasn't very pretty. So let me regroup. So okay, so from this I get that h prime of c, the conclusion, right? Conclusion of Rolle's is that h prime of c is equal to 0 for some c. But now look, h prime of x, by my sum difference rule, right? It's simply f prime of x minus g prime of x. Okay. But now I plug in my c into there, and I have h prime of c is equal to f prime of c minus g prime of c. And this has to equal to 0. That's telling me that f prime of c is simply equal to g prime of c. Now crowning achievement. This is a secant line, and g prime of c is its slope. So that is simply f of b minus f of a divided by b minus a. That's the conclusion of your mean value theorem. Okay, so I'm going to clear this, clear all drawings. And you know what? I'm actually a minute over the official class time, I think. So I think I'm gonna stop here. I'm gonna do another example. I'm gonna record separately some examples on the mean value theorem. And I will see you tomorrow at 5:30 if that works for you. Okay, I'm gonna do the first derivative test. I really will try to keep it to an hour. And then on Friday, I'll do the second derivative test. Okay, all right, you guys, hopefully I'll have a better handle of my tools tomorrow. And okay, if you have any questions, you're welcome to stay and chat with me for a couple of minutes. Other than that, okay, I'll see you soon, okay?